Okay, so section 28.2 is probably the most important single part of this quantum physics section. So I'm going to actually split this video up into two parts. There's sort of the background information and a little bit of practice, and then there's the whole pile of practice problems at the end. So it is kind of a lot. So this idea of the photoelectric effect, we're going to actually, this thing right here, this term, right, photon, you probably heard of it. We haven't talked about it yet. We're actually going to introduce that right after this. Because the photoelectric effect is what explains why you would ever introduce this idea. And so we're kind of doing it back, like the experimental way rather than the other way around. And so the photoelectric effect is sort of the experimental validation of why you might want to consider light as a photon rather than light as a wave. So the first bit here is just talking about what that means, what the photoelectric effect is, what the observed effects are. And then we'll get to the explanation of what it means physically. So the idea of a photoelectric effect is, in some sense, just what the word says, right? Photoelectric, light and electrons, right? We shine light on something, and that light hits these electrons, and then those electrons get energy and bounce off somewhere else, right? They're ejected or kicked off the metal. They're sent flying, basically. And observationally, this is not something you see every day because it was noticed really only when people used ultraviolet light, not visible light. But this right here is your definition, right? The idea of what the photoelectric effect is just anything that causes light to be, or electrons to be emitted due to light. And so this setup right here is a more experimental setup for what you could do to learn about the photoelectric effect. Right? So ignore the battery bit below. Focus on this for right now. So this thing right here is a setup where visually no current can flow. There's a gap between the wires, basically. But if you shine light, right, this light comes down this tube and hits this one thing, if that light is able to get the photoelectric effect to happen, we'll talk about what the requirements on that are in a bit. If the light is able to make the photoelectric effect happen, then electrons will come off of that and they can end up on the other object, and then a current can flow, right? It can go all the way around. And so this thing right here is something that could test the photoelectric effect. And you'll experientially know because you got an ammeter, right? If the ammeter reads 0, that means you don't have the photoelectric effect happening. There's no way for charge to flow in a complete circuit. The battery here is sort of an optional bit. It's not necessary for the photoelectric effect. We'll show what it does later. It's actually a way to sort of measure the strength of the photoelectric effect. But you could take the battery out entirely and you'd still be able to measure something in a current, right? This is like a third source of potential difference in some sense, right? Batteries can provide it. We talked about the motional EMF and things like that with induction. This is now sort of light providing the potential difference in some sense. And so experimentally, we're going to change three things, right? We're going to change what the battery is doing, right? The potential difference. We're going to change properties of the light, the frequency, and the intensity. And we'll see what happens, right? Just for now, we're just going to say what happens if, not try to explain why. Right? So if there's no light, you don't get a current. That's pretty straightforward. But as you change things, you can sort of measure the current as a function of those changes. And so this is just kind of, again, the brief summary of the results you see. Not the why, just the results. Which is this. The more intense the light, brightness, the more current you get. That kind of makes sense. More light means more current. Point 2 seems kind of silly, but we'll come back to why that matters, right? The point is it happens instantly. There's no sort of charge up time or build up or anything like that. It's either once you shine the light, you get the electrons. If the light is not there, you don't get the electrons. Number 3 is weird, right? Number 3 is strange. The first two sort of make sense. But the fact that electrons are emitted only if the light frequency is above a minimum does not make a whole lot of sense in the context of an electromagnetic wave. We'll come back to why that's an issue a little bit later. This is probably the most important one, the sort of special thing that we have to explain. And then point number 4 here is that the value of this minimum frequency changes based on the metal that we have, right? If I change this material, then some light that used to make the photoelectric effect happen won't anymore, or vice versa. And now in terms of changing the voltage, if we make the voltage positive, in other words, sort of try and make the current flow the same way as the light would make it flow, then basically nothing happens, right? It doesn't do anything at all. The battery just kind of doesn't contribute. If we make the battery sort of the opposite, right, negative, so if I make the battery trying to push a current this way, then we do see an effect, right? The current will decrease, sort of like the two are fighting. And at some point, we'll get no current at all, and then it just stays at 0 forever. And this point number 6 is another very strange one, is that the intensity of light doesn't determine when the current goes to 0. And that also doesn't make a whole lot of sense, especially in the context of point 1, right? Point 1 back here, right, this statement, that the current was proportional to the intensity, is sort of logical from what we've explained. But the fact that the stopping potential doesn't seem to affect that is strange. So we have a couple points that are sort of logical and a couple that aren't. And we have to try to make them all consistent. So these are just some graphs. I'm going to go kind of fast through some of this. You can look at the slides on your own. This is a graph that represents the exact same information that was just described, right? The frequency effect and then the battery voltage effect. So a couple fast check ones, right? Why do we get a current at all? Well, if you just had the battery, you don't have a complete circuit. It won't flow. So the battery can't be the source of the current. It really has to be the light, because without the light, you don't have a way to sort of bridge this gap in here. So the light is really the source of the current in a photoelectric effect experiment. So, okay, let's try to then talk about some conclusions based on those observational results. Again, not yet the why, but because of the summary of what this has to mean. This first statement here, this is a chemistry statement, really, right? Electrons are bound to metals. They just stay there. This is, in general, a good thing. So we need to do something to get those electrons away from the metal. That requires energy, right? You can think of it like trying, if you like stick an object with glue to like the floor, you have to pull really hard to get that object to unstick from the floor. But once you get it free, then it'll start flying across the room because you pulled so hard and lost your grip or something, right? Same idea here, right? The electrons are attached to their metals, so it takes energy to get them out. And each metal, just like each glue, it can be different strength, each metal is going to be sort of holding onto its electrons with different strength. That's this idea of this thing called a work function, and that is a term that you need to know for sure. The AP equation sheet, instead of calling it E naught, uses phi, like phi naught or phi for the work function, but you have to recognize the word either way, right? So each metal has a different sort of like grip on its electrons. If you're going to get an electron out of a metal, you need to have an amount of energy bigger than the work function. All right, this is just a reference table of some work functions. Notice the units, electron volts. These are small energies in sort of a everyday scale, but not so much for atomic scales. So the next bit is an energy conservation thing, right? We know that waves in general carry energy, right? So the light waves can give energy to the electrons, and the amount of energy they have left over is given by this right here, right? Which is, this is the energy from light that we gave it, and this is the cost to escape, right? And so what we have left over is then how fast it moves, right? This is energy conservation. That's all it is, right? We put energy in, we pay a cost of that energy, the amount that it sort of takes to get away from the metal, and we have some energy left over. Right? We'll kind of come back to some more calculations with this, so don't worry about the details yet. And so that kind of explains why sort of different intensities of light or different frequencies of light may matter, right? They change the amount of energy you have left. Now, these next couple bits are talking about the battery, right? In general, the electrons are going to scatter in any direction. Not every electron that leaves here makes it there, right? Some will go off and then not hit. So if you don't have a voltage that sort of is the same direction as the current, you don't attract the electrons back. They just might miss. So you're not going to get as much of a current as possible. Right? If you make that end of the battery attractive to electrons, then things that would have missed no longer do, right? They're pulled back up. And so you get all the electrons, but that's why there's a limit, right? Eventually you've caught them all. On the other hand, if you make the anode the opposite, right? You make the battery sort of do the opposite thing, you make it negative, now electrons are being pushed away. And energy conservation can again tell us sort of how this works, right? Let's say if you shoot an electron straight out, right, it's traveling through a potential difference. That's like throwing a ball upwards in gravity, right? It reaches a maximum height and then stops and turns around, right? That's what this sort of describes right here. There's a maximum or a maximally negative voltage at which all the kinetic energy is used up before the electrons make it to the other thing, and that's why the stopping potential ends up being 0, right? And so you can calculate that stopping potential, right, with this, right? So if you know the stopping potential, you know the maximum kinetic energy the electrons had when they were sort of ejected from the surface. And as we saw, if you know this maximum kinetic energy, and you know what metal you have, you can figure out sort of how much energy the light gave it. Or if you know how much energy the light gave it, you can figure out the work function of the metal. But this is all straight from energy conservation, right? Here, we're converting kinetic energy from the light, kinetic energy that the light gave the electrons into potential energy sort of that the light has to, or the electrons have to fight against to go to the other side. That's all it is, just energy conservation. Okay, a couple more practice things. So currently, we have a situation where the battery voltage is helping, right? This end is positive, means this is positive. If we reduce that voltage to 0, what's going to happen? Well, now we had some electrons that would go kind of in a path like this, right? They're getting pulled towards that positive anode. And so now those are just going to keep going like that. And so we're going to have a decrease, but not a removal of current, right? Okay, so that's the experimental result. Those are the things that sort of have to be true for the photoelectric effect to sort of exist as it does observationally. The why is very strange, right? Why do electrons leave the metal? What makes that happen? Why does it depend on frequency? Right? We still haven't addressed that bit at all. And this took Albert Einstein to explain. Actually, well, not just Einstein, but a synthesis of some other ideas that sort of applied to this. So Einstein's explanation of the photoelectric effect was to say that energy had to relate to frequency, right? That's the only way to make that strange statement about that threshold frequency work out, because we've been talking about energy conservation and then somehow frequency appears in that. There has to be a relationship between energy and frequency for the photoelectric effect to work as described. This work by Planck specifically is completely different. It's actually a thermodynamics thing. But we're going to kind of use it sort of the other way around. Planck used energy to explain why you got a certain frequency of light. Einstein is using frequency to explain why you get a certain amount of energy. This letter H, right, this constant, Planck's constant, is very important to know. This is the first constant that only really has relevance in the sense of quantum mechanics. It's sort of like the smallest chunk of energy you can have in some sense. It's not exactly right for the units, as you can see, right? It's not joules, it's joule seconds, but it's in some sense telling you how small a chunk of energy you can have. That equation, that's on the equation sheet with both units. Just notice, right, if you're working with energies in joules, use that one. If you're using energies in electron volts, use the other one. Other than that, very straightforward. So Einstein's suggestion was, well, okay, light has a frequency. Maybe that means that each chunk of light, which is already a weird term when you talk about a wave, each chunk of light has a certain amount of energy associated with it because of that frequency. And so this statement, or these two statements right here, right, the fact that maybe light's not this wave, a continuous wave, but packets or chunks, quantum, right, quantum is the word for like a small piece of something, would explain the photoelectric effect. And he gave the name for a chunk of light the photon. And he said that the energy of a photon is based on the frequency it has. So high frequency light has higher energy as well, which is something that is completely inexplicable with classical physics. And that's the truly important conclusion here, is that this guess cannot fit with classical physics at all. It does not work with a wave model. It only works with thinking of light as a photon. So let's talk about some results of that. So here, if we're doing a photoelectric effect experiment, and we shine red light on it and nothing happens, and we shine blue light on it and we get a current. Why? Well, this is not right because that's a wave, right? This is a wave explanation. A wave explanation wouldn't work, right? If I wanted to give a wave more energy, I should increase the intensity, just make the red light brighter, and eventually it'll work, but that's not what happens. This option C doesn't make any sense either, right? The fewer photons, each interaction is a single photon. D is completely nonsensical. A is the only one that sort of matches our new explanation of what light is that each photon has to have enough energy to sort of get an electron out of the metal. And if red light photons, because red light is a lower frequency light, that means there's also lower energy light. And if it's lower energy light, then that means that you may not have enough energy to sort of get past the work function. Okay. So this one is another sort of example of that. Just a calculation of energy, right? So if we know a wavelength, we can find a frequency, right? That's pretty straightforward, right? Using V, wavelength times frequency, right? We know the wavelength. We know that this is c, the speed of light, because we're talking about light still. That doesn't change. And so we can find the frequency. And then once we know the frequency, we can plug it into our new relationship for the energy of a photon and find the energy from the frequency. Notice we're asked for it in electron volts. So I'm going to pick the H with units of electron volts, not joules. So this is them working that out, right? They calculate the frequency first. Notice, right, always convert to meters, don't use it in nanometers. Then when we know the frequency, we can calculate the energy in electron volts. So with that core statement, right, this first one, that was really the brilliance of Einstein's deduction that explains the photoelectric effect fully. The next two sort of are less revolutionary, but also required. And they just deal with sort of the interaction process, right? And they're kind of the same thing, right? Light interacts with matter as simply like a binary yes or no thing. It either absorbs a photon or emits a photon, or it doesn't. There's no possible way to sort of like half interact with a photon of light or anything like that. That's what both those statements say, is that you either interact with it or you don't. There's nothing in between. This is the idea of the quantization again, right? Whole numbers only. And so now we need to explain a little bit about why this works for the photoelectric effect. So we shine light on a metal. Each photon has a certain amount of energy associated with it. Each photon that hits an electron is absorbed by that electron. So this is the, let me circle out a bit better, right? This is the extra piece, right? This is the piece that was missing from our conservation of energy statement. We didn't have a way to calculate how much energy the light gave an individual electron, but now with Einstein's statements, we do. Each photon goes to one electron, it gives it that amount of energy, HF, right? It gives it its whole energy. You can't just give it part of it. Right, so this picture kind of shows you what that's like. And so now our electrons have energy HF. If HF is bigger than the work function, then by energy conservation, we escape the metal and have energy left over. This is how we're able to get to this threshold frequency, right? If your frequency is too low, you don't give an electron enough energy, and if you don't give an electron enough energy, it can't escape the metal, so you never ever get a current, right? And so all you do to solve for this is you let, right, the leftover energy just equals 0. Right, that's kind of what I just talked about. So the other thing that's important to know, right, intensity for the wave model of light means more energy. But in Einstein's model, a more intense light just means more photons of the same energy. So by making the light more intense, you have more photons, which means you can get more electrons, assuming that each photon has enough energy by itself. If you don't have enough or a high enough frequency, that doesn't matter how intense the light is. You just give a lot of electrons not enough energy. Right? And then so finally, you can relate the stopping potential, right? Again, this is energy conservation. This is what we just talked about, right? HF, the energy you get from light, and the cost to leave, right? You have a certain amount of energy left over. And then this is the conversion between the kinetic energy you're given and the potential energy you need to go through to sort of make it to the other side. And so you can see there's a relationship between V stop and the frequency, right? Which again is not predictable without quantum mechanics. And it doesn't depend on the intensity. Right? So this next bit is just kind of a really fast visual analogy of why quantum mechanics is weird, right? If you throw a pebble into water, right, it makes a splash, and the wave travels outward, and sort of a ton of water molecules get a tiny, 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 tiny increase in energy. But that's the classical view. In quantum mechanics, what would happen would be more like this. You throw the pebble into the pool and nothing happens at all except for a single drop of water goes rocketing out of the pool, flying across the room and hits you in the face. Right? But the rest of the pool is completely unchanged and unaffected. That's weird. That's really weird, but that has to be what happens to explain the photoelectric effect correctly. This work with the photoelectric effect got Einstein a Nobel Prize. Right? It's truly a brilliant supposition because it's one of those things that sort of uses a lot of phenomena, but is sort of incredibly simple once you put that one statement together. All right, so let's do one practice one here, and then we'll pause this and have just the practice slides after. So we're doing a photoelectric effect experiment. Right? Monochromatic, that just means one color or one frequency. And we do get, right, this is a frequency that is able to excite electrons. So the intensity stays the same, but the frequency goes up, right? Intensity stays the same, but frequency goes up. So If the intensity stays the same, that means we have the same total number of photons. So we're not going to get A, right? Each photon can give one electron energy. We got the same number of photons before and after, so we can't have A happen. But increasing the frequency means we increase the energy each photon has, which means we do give more kinetic energy to each electron, which means they have to move at a higher speed. So B is true. So it should just be B. Right? All right, and so we will pause this here, and then the next one will just do some practice problems.